So, I would like to start. Hello, my name is Uchida, and I work in the Data Engineering SATA Data Platform Office at Line. First, I'd like to start by introducing myself. I joined Line in 2018, and since then, I've been working on the development and operation of data platform infrastructure with focus on Hadoop. As we operate Hadoop on a large scale, we often encounter problems and needs for new features that no one has yet encountered. By reporting such problems and features, and by sending patches, we actively contribute to the open source community. Hadoop has two major components: HDFS, which provides the storage function, and Yarn, which provides the computation function. Today, I would like to talk about HDFS. At Line, we are trying to reduce infrastructure costs by utilizing a feature of HDFS called Erasure Coding, which is designed to store data more efficiently. HDFS Erasure Coding is a relatively new feature introduced in Hadoop 3, and we have encountered a number of problems with this in the past. Today, I would like to introduce some of our engineering practices using the data corruption problem that occurred late last year as an example. In particular, the second half of the talk will be about the implementation of HDFS, Erasure Coding, and I hope to show you how fun it is to solve large-scale problems. First of all, I will briefly introduce HDFS. HDFS is a sub-project of Hadoop, is a middleware that provides a distributed file system. It is designed to be extremely scalable and can store petabytes of data distributed across thousands of servers. It is also designed to automatically replicate data to multiple servers so that even if a server dies, the data will not be lost. It is also designed to read and write large amounts of data with high throughput and is widely used worldwide for storage, mainly for data analysis. HDFS consists of two components, name node in master and data node in slave. The name node manages metadata such as the file system and memory. Files are divided into blocks and stored across multiple data nodes. When reading data, for example, the client asks the name node in which data node the data is stored, and then reads the data directly from the corresponding data node. Similarly, when writing data, the client writes directly to the data node, but the data node replicates the block to multiple data nodes to achieve fault tolerance. We in the Data Platform Office provides a unified HDFS cluster for the entire company. We are running one of the largest HDFS clusters in the world in terms of data size and number of servers. A particular note is the amount of data growth, which is averaging about 10 petabytes per month as the service grows and new analysis needs arise. However, not all of the data is used every day, so we are using HDFS Erasure Coding to store older data more efficiently and reduce infrastructure costs. Erasure coding itself is a technology that has been utilized for a long time in RAID and other applications, but it was finally introduced in Hadoop 3 for HDFS. The figure on the left shows how the data store is being used for the conventional replication method, and the figure on the right shows how to store data utilizing Erasure code. In both cases, HDFS first divides the file into units called blocks. In the case of replication, the blocks are simply copied and stored on 3 data nodes by default. In this case, the amount of data is 3 times larger than only when one block is stored. In Erasure coding, this block is further divided into smaller units called cells. In Erasure coding, called RS32 in the figure, 2 partially cells, P1 and P2, are calculated from 3 data cells, D1, D2, and D3, and they are stored in different data nodes. Blocks made up of data cells are called data blocks, and blocks made out of parity cells are called parity blocks. And out of a total of 5 blocks, if 2 blocks are lost, the 2 lost blocks can be recovered from the remaining 3 blocks. So this is the key feature of erasure coding. In the case of RS-23, the amount of data is only 5/3 of the original data, or about 1.7 times. The numbers 3 and 2 in RS respond to the number of data blocks and the number of parity blocks, respectively. So if there are as many blocks as there are data blocks, the remaining blocks can be recovered. In line, we use the default HDFS RS63. Let's look at the data recovery method in more detail. In this replication, we can recover by simply copying the same blocks to another data node. However, in the case of Erasure coding, we need to perform a special process called Erasure Coding Reconstruction to recover the lost blocks from the live block. In the figure, data node 6 retrieved data D1, D3, and P2, recovers D2 and P1, and stores D2 in itself and P1 in data node 7. Here is a table that summarizes the main features of erasure coding and replication. Due to time constraint, I cannot explain everything, but the most important point is that erasure coding is able to store data more efficiently than replication while maintaining higher fault tolerance. In the case of RS63, in the table, erasure coding can store data at half the size of replication, as shown by the storage efficiency. When running erasure coding on a large scale, it is important to be careful about storing small files. In the case of replication, only 3 blocks are generated, but in the case of RS63 erasure coding, 9 blocks are generated even for small files, which increases the load on the namecode. In order to avoid the load caused by small files, Line is applying erasure coding to cold data where the file size can be easily controlled. Currently, we are storing about 12 petabytes of data utilizing RS63. This means that we have been able to save about 12 petabytes of disk space compared to replication. Now I would like to move on to the issue of data corruption and how it was solved at the end of last year. The reason we know this problem was because of a report from a user. This error occurred when the user tried to read an ORC file that had been erasure coded from Hive. Since we could not determine from this error alone whether it was a problem with Hive or ORC or a problem with erasure coding, we decided to thoroughly examine all erasure-coded files. Fortunately, I was able to find an erasure-coded file that produced the same error, but still had a backup, so I compared the 9 blocks of the file bitwise one by one. We found that only 1 block had a different bit sequence. I also traced the history of that block through all the data node logs. We found out that the block had been reconstructed in the past and that a null pointer exception or something similar had occurred in the previous reconstruction. Based on these facts, we decided that there might be a problem with the erasure coding reconstruction. The first thing we do when such an issue arises is to see if there is already a bug reported in the HDFS community. We have found an open issue on HDFS JIRA that is very similar to our observation. To give you an idea of the issue, Stripe Block Reconstructor, the class that is responsible for the main reconstruction logic on the data node, has a static buffer pool that is used for reconstruction. The problem is that the buffer pool gets contaminated under certain conditions, and the blocks reconstructed utilizing the contaminated buffer pool get corrupted. In order to understand the condition under such a contamination occurs, let's look at the reconstruction mechanism in detail. the stripe block reconstructor performs reconstruction for each buffer size, 64 kilobyte by default. First, before starting reconstruction, stripe block reconstructor create an object called stripe block leader to read the blocks on the data node. In doing so, the reader gets a buffer from the reconstructor's buffer pool. Then, in each iteration, the reconstructor commands the reader to read data from the source data node, and the reader reads the data into the buffer. After all readers have finished reading, reconstructor will reconstruct the data in the buffer. The reconstructed data will be transferred to the target data node by the stripe block writer. At the end of the iteration, the buffer is cleared. When all iterations are done, the reader returns the buffer to the reconstructor's buffer pool. Now, let's see how the buffer pools get polluted. This problem occurs when a stripe block reader times out. When a reader times out, a new reader is created to read the data from another data node. After reading the minimum number of readers required for reconstruction, the timeout reader will be canceled. Then, in the next iteration, when the reconstruction gets the result from the reader, null pointer exception will occur and the reconstructor will fail. The reason for the generation of null pointer exception is because of the poor handling of the reader, which was canceled due to timeout. But for the detail, we need to follow the source code, so I would omit going through the explanation. When the reconstructor finishes, it will order the reader to return the buffer to the buffer pool before closing the reader. However, if this is done, the reader will continue to read data until it is closed, since it will continue to hold the buffer even after returning it, which will contaminate the buffer pool. Since the buffer pool is defined statically, in the next reconstruction, probably of another block, another stripe block reconstructor will use the tainted buffer pool to perform the reconstruction, resulting in the creation of a broken block. This is a scenario in which a corrupt block is created due to a tainted buffer pool. By reading the source code, we were sure that this bug was the cause of the file corruption, so we decided to patch it. So patching is not the end of the story. There are two major issues that needed to be addressed. How to monitor that data corruption was no longer occurring after the patch was applied, and how to prevent data corruption in the future, taking into account the possibility that other bugs may be lurking or new bugs may occur in the future. For the first one, data corruption detection, we decided to use Spark to save the checksum of the erasure coded files as a Hive table on a daily basis and compare them. The implementation was done quickly, but when we actually ran the job, we encountered a few unexpected problems. The first was a file descriptor leak on the data node when retrieving the checksum of the erasure coded file, and the second was that it returned a wrong checksum value. Both of these issues are still unreported, so we have sent patches to the HDFS source code. So let's take a closer look at these two issues. When getFileChecksum is called for a file that has been erasure coded, the figure shows that data node 1 gets the checksum of the data blocks from other data nodes and calculate the checksum of the file from those blocks. If a checksum for a block cannot be obtained due to a timeout or other reason, data node 1 reconstruct the block from the live blocks that and calculate the checksum. The problem of the file descriptor leak was caused by the fact that the connection to the data node used in this reconstruction was not closed. The problem of getting the wrong checksum was also caused by this reconstruction. Using the figure as an example, when reconstruction fails due to not obtaining P1 and P2 because of timeout, getFileChecksum ignores D3 and calculates the checksum of the file from D1 and D2 alone. As for the second issue, how to prevent data corruption in the future, we implemented a validation logic to check the correctness of reconstruction at every reconstruction and sent the patches to the HDFS source code. This feature has already been merged upstream and is enabled by setting the property EC reconstruction validation to true in HDFS file.xml on the data node. It also provides a matrix called EC invalid reconstruction task, which can be used to detect validation failures. The idea is to use the reconstructed block and run the reconstruction against for validation. For example, if D2 is lost in the figure, the data node will reconstruct D2 utilizing D1, D3, and P1. But our patch will continue to reconstruct D1 utilizing the reconstructed D2. If the D1 obtained here, in other words, D1 prime in the figure, does not match the original D1, then there is a bug in the reconstruction and the reconstruction will fail. As we have seen, bugs mostly occur under special conditions. In the case of data corruption caused by dirty buffer pool, it was triggered by a timeout in reconstruction. Our patch allows to stop the generation of broken blocks by failing the reconstruction until the condition is resolved. This validation does not guarantee 100% correctness of the reconstruction, but we believe it is very effective against similar bugs. It has been almost a year since the patch was applied, and our monitoring systems have not detected any data corruption since then. Since we used to expect one file corruption every few days, we can at least say that the data corruption bugs have been resolved. However, when we try to guarantee the correctness of erasure coding on a larger scale, the current method of periodically obtaining the checksum of all erasure coded files is not very practical, since the execution time will be longer depending on the number of files. This is not very practical. In the future, we feel it is necessary to have a mechanism to monitor the checksum of the block to get it in real time for each event, such as reconstruction. Now I would like to summarize. HDFS erasure coding works well most of the time, but bugs often appear in a large environment. In this case, I don't think it is mature yet. If you're considering utilizing erasure coding, it is recommended that you use the latest maintenance version of HDFS as much as possible and that you check the JIRA of HDFS periodically. In closing, I would like to continue to contribute not only to HDFS, but also to various OSS and to build a better data platform together with engineers around the world. Thank you very much.